Today we'll look at section 12.2, logarithmic functions. Logarithm. For any positive real number, b not equal to 1, and any positive real number x, we define log base b of x as the power that b must be raised by to equal x. Log base b of x is pronounced the logarithm base b of x, or we can say log base b of x. For example, we have log base 3 of 9. What is this equal to? Well, this is what power do I need to raise 3 to get a 9? The answer to this log base 3 of 9 is the exponent that we need. So we know that 3 squared is equal to 9. So log base 3 of 9 is equal to 2. That's the exponent that we need. Again, the answer to the logarithm is the exponent. For any positive real number, b not equal to 1, and any positive real number x, we define f of x equals log base b of x as a logarithmic function. The function f of x is defined only for values of x greater than 0. So the domain of our function is from 0 to infinity. Let's evaluate some logarithmic functions. Part A, we're looking for log base 2 of 8. The base is 2. What exponent do we need to raise 2 by to get an 8? Well, that implies that 2 cubed is equal to 8, and that means log base 2 of 8 is 3. Now, try the next examples on your own and see if you know how to evaluate logarithmic functions. In the next example, we're asking 4 raised to what power is equal to 16? I know 4 squared is equal to 16, so log base 4 of 16 is equal to 2. In part C, we're asking 12 raised to what power gives us a 12, and so the exponent is 1. That means log base 12 of 12 is equal to 1. In part D, 3 raised to what power gives us a 1 over 27. The exponent has to be negative, and I know 3 raised to the negative 3 is equal to 1 over 27. And this means that log base 3 of 1 over 27 is equal to negative 3. In part E, 5 raised to what power gives us a 1. 5 raised to the 0 gives us a 1. That means log base 5 of 1 is equal to 0. Again, recall anything raised to the 0 power is equal to 1 except 0. Example 2. Given the function f of x equals log base 2 of x, find f of 16. We'll start by writing f of 16 first. And that means I need to do substitution. This is a substitution problem now. We'll plug in that 16 for the x. Log base 2 of 16. 2 raised to what power is going to give us 16? I know 2 cubed is going to give me 8. 2 to the 4th is going to give me 16. So this is a guess and check kind of game. And I guess that 2 to the 4th power is 16. So log base 2 of 16, that's equal to 4. Part B, we're finding f of 1 over 256. F of 1 over 256 is equal to log base 4 of 1 over 256. I use a parentheses around the argument so the reader knows that 1 over 256 is the entire argument. Now we'll have to guess. 4 raised to what power is going to give us a 1 over 256? Let's try 4 to the 4th, and that's 256. Using my calculator, I know that 4 raised to the 4th is equal to 256. So that means in order to get a fraction, we need a negative exponent. 4 raised to the negative 4 gives us that fraction 1 over 256. And so log base 4 of 1 over 256 is equal to negative 4. And that's just using our calculator, checking to see what exponent works. I know 4 to the 4th is 256, but we needed a fraction. That's why we use negative 4 to give us a fractional answer. Part C, let's write f of 3,125. We'll do the substitution into our logarithmic function. And we'll have to guess. 5 to what power gives us 3,125? I'll go on to Desmos. 5 raised to the 4th is too small, so we'll check again. Let's try 5 raised to the 5th. 3,125. 3,125. This means log base 5 of 3,125 is equivalent to 5. We define the common logarithm whose base is 10. We write log x rather than log base 10 of x. So if you see inside the base of a log, there's nothing written, it implies that the base is 10. When I write log of 5, there's nothing written here, it actually means log base 10 of 5. So that's something to remember. If the base is missing, automatically assume it's an invisible base 10. In example 3, evaluate the given logarithm, round to the nearest thousands if necessary. In part A, it's written log of 100. This means log base 10 of 100. So 10 to what power gives us 100? And that is 2. 10 squared gives me 100. Log base 10 of 100 must be equal to 2. In part B, again, the base is an invisible 10. 10 to what power gives us 10,000? And you could quickly check that with a calculator. I know 10 to the 4th is going to give me 10,000. That means log of 10,000 is equal to 4. In part C, it's more difficult to do that by hand, but it is possible. 10 to the 1st is going to give me 10. That's too small. 10 squared is going to give me 100. That's too big. So I know log base 10 of 75 is going to be between 1 and 2. So you could get closer and closer by estimating different exponents, but in real life we actually use calculators for these examples. Log of 75, I'll have to use my scientific calculator for that, so I'll use Desmos. We'll go to desmos.com/scientific and write log of 75. Log of 75 is 1.875. So we'll write 1.875. This is approximately 1.875. For part D, we'll again check with our calculators. We can approximate this log of 0.01. And this gives me a -2. Sometimes we don't use a base of 10, we use a base of e. The natural logarithm, denoted with ln x, is a logarithm whose base is e. Recall e is an exponential constant located on your calculator. It's approximately 2.718 and so on. So when we write the natural log of x, you know this is log base e of x. Again, if it's written as ln x, assume that the base is e. If it's written log of x, like the previous examples, the base is assumed to be 10. So that's the difference. If it's log x, the base is 10. If it's ln x, or the natural log of x, the base is assumed to be e. For these, we'll have to use our calculator. Part A, we're looking for the natural log of e to the 7th. So let's use our calculator for that. We'll write ln, and then we'll have the base of e is already included in the calculator, so we don't need to write that. Type in e raised to the 7th, and our solution is 7. The natural log of e to the 7th is 7. And that makes sense because the natural log of e to the 7th is equivalent to log base e of e to the 7th, which implies e to what power is equal to e to the 7th. So think about that for a moment and you'll clearly understand that that exponent has to be a 7 because the base is the same. And that's why the natural log of e to the 7th is equal to 7. Let's try the natural log of 65 on our calculators. This gives me 4.174. And in part C, you can use your calculator, or you can use example A as a guide. This is equivalent to negative 1.77. In part D, I'll have to use my calculator for this. Let's look for the natural log of 27.3. And that's 3.307. Again, I'm rounding that up to 3.307 with my decimals calculator. But you could use other scientific calculators and should get the same result. There's a property of logarithms, and we saw this in example A. Log base b of b raised to the r is equal to r. You can think about this question. Log base b of b to the r is asking us b raised to what power gives us b to the r. And that is why this r is our solution, because that's the exponent. For a logarithmic expression, the answer is always the exponent. And so this property always holds true, that if you have the base b here, and the argument being a base b raised to r, the solution is always the exponent r. Now let's convert back and forth between exponential form and logarithmic form. Here is exponential form. B raised to the x is equal to y. That's exponential form. For logarithmic form, we're saying log base b of y is equal to x. Notice how x is our exponent. The answer to the log is always the exponent, and the b here is our base. So remember, for the logarithm, the exponent is always the answer to the log. Let's write the following in logarithmic form. We'll write this as log base, and in this case the base is a base of 2, so I always start with that first, and then I put an equal, and I know the answer to the log is always the exponent, so that gives me a -8 out here, and the argument is that 1 over 56. So we'll put 1 over 156 here. For part B, I'm going to write log, and the base here is the 7, right? The base is the 7, so we'll put that here. I leave myself some space, and I will put in the exponent. The exponent is always the answer to the log. That's how I remember these things. And that gives us that 25. That 25 has to go inside the argument. Log base 7 of 25 is equal to x. In part C, I'll start with the base. Always start with the base. The base is 3. And we always remember the answer to the log is the exponent. And that leaves us with the argument here of 350. For part D, the base is 5. We'll start with the 5. Leave us some space, and the exponent is always the answer to the log. So this is log base 5 of 1 over 125. And that is the logarithmic form. In example 6, we want to go backwards. We want to rewrite this in exponential form. And so that means we want to rewrite it as b raised to the x is equal to y. We're converting it to this exponential form. To do this, I always start with the base. The base is right here. The base is 3. So we're saying 3 raised to the exponent. But I remember that the exponent is the answer to the log. This is 3 raised to the 6 equals x. And that's the exponential form. For part B, what's the base? Well, the base is e, because for natural log, the base is assumed to be e. So we can write this as e raised to the 7 is equal to x. For part C, we have a log without a base. That means the base is an invisible 10. I can write this as 10 raised to the exponent, which is x, equals 100. In part D, we have the base is 2. We'll raise that to our exponent, and that should give us our argument 128. And now we can convert back from exponential to logarithmic, and then we could do logarithmic to exponential. So why do we need to learn how to do that? Well, it's to solve logarithmic equations. The tip here is to rewrite your equation in exponential form. Always rewrite your equation in exponential form so you can solve for x. Let's look at part A. We'll rewrite this into exponential form first. This is written as 5 raised to the 4th is equal to x. And we could evaluate 5 to the 4th. 5 raised to the 4th is 625. And so, x is equal to 625. In part B, I'll translate this into exponential form as 7 raised to the -2 equals x. And I know 7 raised to the -2 is equivalent to 1 over 7 squared, which translates into 1 over 49. In part C, we'll translate this as a base of 10. This is 10 to the 5th equals x, and we can simplify that as 1 followed by 5 zeros. X is equal to 100,000. For part D, a lot of students make the mistake of not isolating the logarithm first. That's what we need to do first. So start by subtracting the 5 to both sides, and that will isolate the logarithm. This is log of x equals 7, and then we can translate it with exponential notation. The base is 10 because log implies a base of 10. 10 to the 7th is equal to x, and that means x is equal to 1 with 7 zeros after it. And this is 10 million. X is equal to 10 million. In example 8, let f of x be equal to the natural log of x minus 8. I want to solve f of x equals 3 and then round to the nearest thousandth. A lot of students make the mistake of substituting in a 3 for x. This is not what the question is asking. I actually want to replace f of x equal to 3. This f of x is replaced by 3. We're not substituting a 3. This is not f of 3. That's a different question. So what we want to do is rewrite this as 3 equals the natural log of x minus 8. And I want to solve for x. To do that, we'll translate this into exponential form. What's the base? The base is e. So we'll rewrite this as e cubed equals x minus 8. To solve for x, we'll add 8 to both sides. And x is equal to e cubed plus 8. This is a good solution, but we should round our answer to the nearest thousandths. Let's type this on Desmos. E raised to the 3rd power, and then we need to add 8 to it. So our solution is 28.086. 28.086. That's our solution according to Desmos. Let's look at part B. Again, this is finding f of x equals to 3. We're not substituting. We're not doing f of 3. We're replacing f of x with 3. So let's rewrite this as 3 equals log base 5 of 3x minus 1. Translate it with exponential notation. The base is 5. The answer to the log is the exponent. That's 5 cubed. 5 cubed is equal now to 3x minus 1. I know what 5 cubed is. 5 cubed is 125, and that's equal to 3x minus 1. We can add that 1 to both sides. So this is 126 equals 3x, and I can divide both sides by 3. And we should get x is equal to 42. In example 1, let's graph f of x equals log base 2 of x and also state our domain and range. Before we start graphing it, I like to replace the f of x with y just to make it easier to graph. Y is equal to log base 2 of x. Now it's really difficult to graph log base 2 of x, so we'll rewrite this in exponential form. The base is 2, the power is y, and this is equal to x. So this is the exponential form of our logarithmic function. So we'll create a table now. And I'll have x and y here, and I will actually pick values for y. If you plug in a value of y, you get x. if you plug in values for x, it's very difficult to solve for what y is. So we'll just plug in some numbers. Let's say -2, -1, 0, 1, and 2. What is 2 raised to the -2? That's going to give us 1/4. And you could check that with a calculator. 2 raised to the -1 is going to give me 1/2. 2 raised to the 0 is 1. 2 raised to the 1 is 2. And 2 squared gives us 4. We'll be able now to graph the values of this logarithmic function. 1/4, comma, -2. 1/2, comma, -1. 2, comma, 1. 4, comma, 2. So this is our logarithmic function. It looks kind of like an exponential function, but it doesn't have a horizontal asymptote. It actually has a vertical asymptote. So we have a vertical asymptote for this logarithmic function with a base of 2. What is the domain? This function goes to the left to 0, but it does not touch 0. It gets closer and closer to this vertical line, but it doesn't touch it. It goes to the right forever. For the range, it's from -infinity to infinity. It goes down forever and up forever. Let's try example 2. Again, we'll use the same process. We'll rewrite this as y equals log base 4 of x. And then I'll translate this to exponential notation. The base is 4. The exponent is y. And this is equal to x. So I will pick some values of x and y. And you can tell it's easier to plug in the y. So let's pick values -1, 0, and 1. Now, why did I pick just these values? I know that if I pick -2 or 2, we're going to get values that are quite large, and it might not fit on our graph. So we only need 3 points because we know the general shape for a logarithmic function. 4 to the -1 is going to give me 1/4. 4 to the 0 is going to give me a 1. And 4 to the 1 is going to give me 4. You could definitely pick more points, it just might not fit on your graph. 1/4, comma, -1. 1, comma, 0. And 4, comma, 1. So we have this logarithmic function. It looks kind of like a hockey stick, but we want to include that dashed line. That's our vertical asymptote. And the domain and range is exactly the same as the previous example. It goes left to 0 but doesn't touch 0. It goes to the right forever. The range is from -infinity to infinity. It goes down forever and up forever. In example 3, we're going to graph log base 1/3 of x, and we'll also state the domain and range. Now for this question, we'll do the same process. We'll rewrite this as log base 1/3 raised to the x. Translate this as an exponential. The base is 1/3 and the power is y. 1/3 to the y is going to give us x. And we'll make a table again. It's easier to pick the y. So we'll put -1, 0, 1. Plugging in these values into the calculator, 1/3 to the -1 is 3, 1/3 to the 0 is 1, and 1/3 to the 1 is 1/3. So what happens when the base is less than 1? Let's see what that changes in our logarithmic function. It's 3, comma, -1. 1 comma 0, and 1/3 comma 1. So what happens? It actually flips our logarithmic function upside down, and it does affect the graph. It does flip it upside down. Instead of going upwards, it's declining now. But if you look carefully, the domain is still 0 to infinity, and the range goes negative infinity forever down and up to infinity. So the domain and range is still the same, even though it's going downwards. In example 4, let's graph log base 2 of x and f of x equals 2 to the x on the same set of axes. So I'll start by graphing y equals 2 to the x first, and we'll just make some points on the graph here. I want to pick negative 1, 0, 1 for the x because it's easier to plug in x and then solve for y. 2 to the negative 1 is 1/2. 2 to the 0 is 1, and 2 to the 1 is 2. So we'll plot this on the graph. Negative 1 comma 1/2, 0 comma 1, and 1 comma 2. So this graph is a increasing exponential function. For the other one, we'll rewrite it as y equals log base 2 of x by replacing f of x with y. We can translate this as an exponential function as 2 raised to the y equals x. And then we'll make a table. So to graph logarithmic functions, you just have to do an extra step. We'll pick y values, and you'll see something interesting. 2 to the negative 1 is 1/2. 2 to the 0 is 1, and 2 to the 1 is 2. So compare this table with our new table, and you'll see something. Logarithmic functions and exponential functions are inverses. They're inverses of each other. So that's important. Let's graph the inverse. 1/2 comma negative 1, 1 comma 0, and 2 comma 1. So you can see that a logarithmic function with the same base is the inverse of an exponential function with the same base. They're symmetric about this line, y equals x. And how is that important? That's important now because we can solve logarithmic functions using inverses. That is very important in the next section. Let's look at example 5. The number of U.S. airports in a particular year can be approximated by the function f of x equals 14,650 plus 1,344 natural log of x, where x represents the number of years after 1979. Use this function to predict the number of U.S. airports in 2030. To do this, we'll plug in the time. So how much time has passed from 2030 from 1979? So to do this, we need to do subtraction. And if we do the subtraction, we get 51 years. It takes 51 years from 1979 to 2030. And that's what I want to find. I want to find f of 51. And that means we need to plug in the 51 into our function. And to do this, we'll type this entire thing into our calculator. We'll type in 14,650 plus 1,344 times the natural log of 51. So let's enter that into our calculator. 14,650 plus 1,344 times the natural log of 51. And I got a number 19,934.3. So let's just round that to 19,934. And this is the number of airports that we will have in the US in the year 2030. In example 6, the average height in inches of girls who are 3 years old or younger can be approximated by the function f of x equals 18.6 plus 4.78 times the natural log of x, where x represents the age in months. Use the function to determine the average height of girls who are 24 months old. In example 6, we'll look for f of 24. We're going to substitute that 24 into our function. And we'll round this to 1 decimal place to see how many inches a 24-month-year-old girl is supposed to be. We have 18.6 plus 4.78 times the natural log of 24. And we have approximately 33.8. That means our 24-month-year-old girl is approximately 33.8 inches tall. In example 7, the percentage of U.S. workers who drive themselves to work can be approximated by the function f of x equals 72.5 plus 2.01 times the natural log of x, where x represents the number of years after 1984. Use this function to predict what percentage of U.S. workers will drive themselves to work in 2031. To do this, I will have to find the number of years between 2031 and 1984, and that's a subtraction problem. And that gives us 47 years. So we know we'll plug in a 47 into our function. F of 47 is equal to 72.5 plus 2.01 times the natural log of 47. So we'll enter this into our calculator. So we have 72.5 plus 2.01 times the natural log of 47, and that gives us 80.2. And so this is equal to 80.2%. This represents the number of U.S. workers who drive themselves to work in 2031, about 80.2%.